session. So Maria Grazia will start by a review on GRB. Go ahead.
Yeah, thank you, Olivier, and thanks to all the organizers for inviting me to talk to this very broad topic. So, of course, GRB observations is a very broad topic. I try to make some selection, try not to overlap too much with other great talks that you will hear in the complementary observation session that will probably touch more in detail some aspects of radio and X-rays and high energy emission of gamma ray burst. So I will give you an overview of gamma ray burst observation in the context of multi-messenger era with multi-messenger astronomy with gravitational waves, let's say. So first of all, since this is an heterogeneous audience, I give you some basic hints about what a GRB is for those who are not familiar with that. So gamma ray bursts, GRBs, are the most powerful electromagnetic sources in the universe. When a gamma ray burst explodes, it outshines the gamma ray sky, and usually the first initial signal that we receive from gamma ray burst, it's called prompt emission. Its duration is from milliseconds up to minutes. It's very, very bright and peaks. Its emission, its spectrum peaks at energies that are between keV up to GeVs. And as you can see here, the light curve, the shape, how it evolves in time can be very different and very sparse, with usually a lot of temporal variability. This prompt emission phase is followed by the so-called afterglow that is a smoothly decaying, let's say smoothly, you will see it's not completely true, decay of the flux in time over time scales that, depending on the energy at which we observe them, can be from minutes up to hours and also days, and more than many days, let's say. And this emission can be observed in at all the energy of the spectrum, from GeV to X-rays, UV, optical, infrared, and radio. Here you can see a very beautiful example where you can have emission from, as I said, from GeV to radio band at different times. So a little bit of history. Gamma ray bursts were discovered and announced in the 70s by the Vela satellites. But since the 90s, we started to collect physical information, basic information about their nature and their emission. And this is mainly due to the data collected by two instruments, BATSI, and the instruments on board the Beppo-SAX satellite. So these two missions, Compton Gamma Ray Observer with BATSI and Beppo-SAX, gave us a general overview of all the properties of gamma ray bursts. And in particular, they discovered their extragalactic origin, the existence of two families, as I'm going to show you, of short and long gamma ray bursts, and characterized the prompt emission in the case of BATSI, while the possibility of Beppo-SAX to repoint narrow field instruments to the location of the gamma ray burst at other wavelengths, softer wavelengths after the discovery of a gamma ray burst, enabled us to discover that there is indeed a counterpart, the so-called afterglow that I mentioned before, and to locate more precisely the gamma ray burst, to enable the measure of the redshift, and demonstrated indeed the extragalactic origin of these events, and also discovered the association of the so-called long gamma ray burst with supernovae, core collapse supernovae, providing the smoking gun for the progenitors of long gamma ray burst. After that, we had other successful missions that opened new windows in gamma ray burst science. For example, 82, who enriched our knowledge of other families of gamma ray burst, and also contributed together with SWIFT to the discovery of the equivalent of that happened for long gamma ray burst, the afterglow of short gamma ray burst. Then, as I mentioned, we had SWIFT and Fermi that are currently the main missions devoted to gamma ray burst science, and that gave us most of the information that we have up to now. I'm going to talk about that. And I just want to briefly mention that we are living in an exciting time because, as all of you know, since 2017, we are really living the multi-messenger era with gravitational wave. And also, we opened a new exciting window in gamma ray burst science, discovering very recently, thanks to MAGIC, S, and LASO, the very high energy counterpart to gamma ray burst. So as I said, since Bazzi, we discovered that gamma ray bursts could come in two flavors, short and long gamma ray burst. This comes from looking at the distribution of the duration of the prompt emission. So the distribution was bimodal in Bazzi data with a dividing line at 2 seconds, which is conventional. And apparently there are these two families that comes out only from this phenomenological observation. So these short and long gamma ray bursts are not only different in duration, they look different also in spectrum, with short gamma ray bursts harder than long gamma ray burst. And when we had redshift, so we can compute physical quantities associated to the observed ones, we can see that short gamma ray bursts are indeed different from long gamma ray bursts, being usually less energetic and spectrally harder. This is a very famous plot for GRB people. It's correlation between peak energy of the prompt emission spectrum and its total energy or the peak luminosity of the prompt emission. And as you can see, short and long usually distributes in different regions of this plane, while in luminosity, short and long, they appear to be much more similar. So these two families are not phenomenologically different at I, but they are physically different somehow. This difference is even more evident when we look at the X-ray counterpart. So short gamma ray bursts, again, have a fainter X-ray afterglow. You can see here the comparison of short and long GRB afterglows observed by Swift. Short gamma ray bursts are usually at least 2 orders of magnitude less bright in X-rays. However, if we normalize the X-ray emission by the isotropic energy, so as I said, the isotropic energy is lower for short gamma ray bursts, they tend to be very similar. So everything depends, their difference depends from the fact that usually they are less energetic. This is not the only thing that we knew about short gamma ray bursts and long gamma ray bursts. So up to now, we are talking about phenomenological hints, but actually there are also evidences that come from GRB observation that points to very different to underline the difference of these two families. For example, looking at the ambient redshift distribution and also the properties of the host galaxies of long and short gamma ray bursts, their difference is even more manifest. In fact, if you look here, for example, the redshift distribution of long in gray and short in dark, let's say black, in black, you can see that for Swift gamma ray burst, as you can see, they are very different. So short gamma ray burst peak at 0.5, 0.8 redshift, while long gamma ray burst peak at 2 and extends to much higher redshift. More than that, long gamma ray bursts follow the star formation rate with some caveats, while short gamma ray bursts, distribution follow a delayed star formation rate, which again points to some physical difference that is more related to the progenitor. If we look at the host galaxies associated to long and short gamma ray bursts, now thanks to Swift, we have a huge sample of long and short gamma ray bursts with precise localization that enabled to really make this kind of comparison in a statistical sense. Long gamma ray burst hosts are young, less massive, and with high specific star formation rate. You can see here, this is the distribution of the specific star formation rate for long gamma ray burst, which appear very different from short gamma ray burst that, on the contrary, explode in all types of galaxies. So also long gamma ray bursts are, when well localized, they appear to explode where the hosts are very bright, while short gamma ray bursts explode in a different sites. So this combination points to the fact that long gamma ray bursts are usually associated to young stellar populations, while short gamma ray bursts are associated to old stellar population, and their explosion site is not representative of the progenitor per site. So what do you think about that? It means that these two populations are really produced by different progenitors. This kind of idea was supported very soon, as I said, by Beppo Sachs in the late 90s for long gamma ray bursts, that being more brighter, they have been and they could be studied more in detail from the very beginning. And in fact, long gamma ray bursts were very soon associated to the explosion of supernovae, type 1b/c core collapse supernovae, and this association was spectroscopically confirmed in 1998 and then tested in many, many cases where the GRB was so close that we could indeed search, and we found supernovae associated to them. Short gamma ray bursts were more elusive, fainter, so their discovery of the afterglow and their localization arrived very, very late. But even if from the very beginning, when we looked for supernovae, we never found one. You can see that limits put on the supernova emission associated to a possible short gamma ray burst is very well below to the typical magnitudes of long gamma ray burst supernovae. And in fact, in 2013, associated to a short gamma ray burst, we identified in the light curve, in the in the infrared light curve of this short gamma ray burst, an excess that was at the time associated to another kind of transients, the so-called kilonova, and Daniel will explain to you everything about kilonovae. Just I want to mention that kilonovae are transients that are usually thought to be associated to the merger of two compact objects. So not a smoking gun, but since then we found in many, many cases chromatic excesses in short gamma ray bursts afterglows that can be related to this kilonovae. So you can see we have old stellar population, not representative of the birth site, kilonovae, everything for short gamma ray bursts led us believe that the progenitor was the merger of two compact objects with at least one neutron star. And this was well before 2017. And in fact, yeah, everyone knows that, but I had to put it, sorry. Indeed, even we were very well prepared for this discovery, we finally had this smoking gun of the short gamma ray burst progenitor in 1708-17, so the first short gamma ray burst associated to a gravitational wave signal, actually the only one up to now, and the only electromagnetic counterpart discovered associated with a gravitational wave signal. So this was a clear proof that the binary merger of two neutron stars led to the production of a short gamma ray burst. Not only to that, but also the first time that we directly observed a kilonova associated to the same objects, gamma ray burst, gravitational wave, and this time we could even have a spectroscopical measurement of the kilonova. So this is the first and only one spectroscopically identified kilonova. So this event is very important because it marked the birth of the multi-messenger astronomy with the gravitational wave. But not only that, for GRB people, actually, it's even more important because we really had the proof of many, many things that we could retrieve from observations up to that moment, but we could not see directly. Meaning that this new messenger gravitational wave really enabled us to see gamma ray burst in a deeper way, in a different way, giving us complementary observations and information. So what is the current paradigm for gamma ray burst? So I show you some phenomenological stuff, but we have a sort of physical explanation for all of that. Actually, if you work in gamma ray burst, you know that this is not true. It's never true, but still, let's say that we know now that the two flavors are really two different families. They come from different progenitors. So short gamma ray burst comes from the merger of compact objects that contains at least one neutron star. Long gamma ray burst comes from the core collapse of a massive star, very special massive stars, not all, this is another open problem. But regardless of the progenitor, in both cases you end up with a central engine that is a compact object and an ultra-relativistic outflow, collimated, so a jet, and shocks within the jet at the very beginning from shells that moves with different Lorentz factor, produce the prompt emission with this high temporal variability, while when the jet decelerates and starts to interact with the interstellar medium or the circumbust medium in general, you can have the production of the afterglow that is smoothly decaying and moving in frequency from GeV to radio frequencies. Of course, this is not that simple, and in fact, actually Swift, looking at X-ray, early time X-ray emission, discovered that the temporal variability of the X-ray afterglow is much more complex than we thought before, Swift, with the presence of rebrightening, plateaus, different time breaks. And I cannot enter into many details, but we will have a talk about that by Clara in the next days. All this phenomenology was related to the activity of the central engine. So the central engine, I said, as a general statement, is a compact object, an accreting compact object that should power the prompt emission and this outflow, relativistic outflow. But we don't know exactly, and two possibilities what it is. And two possibilities are magnetars that are currently competing with black holes as source of GRB power. And I'm sure Clara will show you how to relate this observation to the central engine. Talking about the ultrarelativistic jet, its composition and structure are currently very poorly constrained. So other observation, and especially high energy observation, that are now enabled thanks to the MAGIC, S, and LASO, but in the near future we will have CTA that will increase our knowledge of the spectrum at very high energy, will help us to constrain the composition of the jet. And concerning the structure, I know that Clément will talk about that later. Thursday, I think. But for the moment, we up to 1708-17, we thought that the jet was the so-called top hat jet. So a uniform, well-established jet without any wings and without everything. Actually, this event was so interesting and important for GRB people because it represented also the first direct observation of the jet structure. Actually, if you look at the X-ray emission of this event, compared to the typical X-ray emission of short gamma ray bursts, you see already that it's very different. And people just looking at that interpreted this scenario as a GRB seen slightly off axis. So you don't see the jet inside the core, but you see the jet a little bit from outside. And this helped a lot with the multi-wavelength modeling of this GRB emission, helped a lot to constrain the structure, showing that actually this jet has wings with decreasing Lorentz factor and decreasing energy content. But the real and direct measurement of that came from the radio observation of this event, actually VLBI observation of this event that demonstrated for the first time that not only the source moved with a proper motion, but also allowed to measure the structure of the jet. So we now know that in this specific case, the jet is structured with a relativistic core of aperture of 5 degrees and wings that extends well beyond that. And we are looking at that at about 20 degrees from the axis of the jet. But I'm sure that Stefano, you will talk about that, I guess, more in detail. So thanks to this single event, we had the final proof for short gamma ray burst from short gamma ray burst progenitor, the final proof of the existence of a kilonova, and it looks like how we expected. And Daniel will explain that much better. The final proof that the emission of gamma ray burst is not only collimated, but is structured, and this is the structure. But still, we have just one case. So in this field. So I just put here a few key points that, in my opinion, are very important in gamma ray burst observation that enabled us to arrive very well prepared, because this was one case that explained to us a lot, but just because we already had a lot of years of gamma ray burst observation. So the first key point is having a triggering facility that is capable to discover and localize gamma ray burst. Discover and localize gamma ray burst is, and this is necessary, as I said, because you have to look at this at all possible wavelengths, spectroscopy, photometry, whatever, and also to spot in time of gamma ray burst afterglow, but also the possible associated kilonova or supernova to point directly to the progenitor of the event. Then, realization must be disseminated publicly and rapidly. And this is because rapidly is decaying in time very fast, and possibly you want to have also redshift. Okay. Sorry. You want to have the redshift measured in most of the cases, because only with redshift you really can measure and compare physical properties associated with gamma ray burst. And of course, you want to monitor at all wavelengths with different external facilities that you want to involve in this game, let's say. So this, I put here this very brilliant example of how the precise localization of Swift in one specific gamma ray burst that was actually not discovered by Swift. So from the EPN localization, which was very much broader, Swift XRT mapped all the region with tiling and actually spotted the counterpart, located that, the X-ray counterpart, and this allowed JWST to repoint the location and to discover a kilonova associated to this event. So it's an example, very brilliant, of how the precise localization, the rapid dissemination, and the synergy of different instruments and facilities allow to discover a lot about this gamma ray burst. And this gamma ray burst is very interesting. I will tell you more about that later. Also, another lesson that we actually learned from Swift in 20 years of activity is that the data, the information must be publicly accessible. So I put here just this brilliant example of the Swift repository in UK, where you can find all the information about gamma ray burst data. You can play with your data. You can use all the Swift observation for your science, and everything is made public and available. Then when you have a lot of observation, you have to manage them in a proper way. So even if you have large sample that enables you to do statistical studies, you don't want to do that without some criteria. And as I said before, one thing is to have redshift measurements because you want physical quantities, but also you need to build samples that are representative of the population of gamma ray burst that you want to study. And I put here an example that we did a few years ago, and we are updating in our group in Merate, is building complete samples of events with, in this case, with favorable conditions for the ground-based observation, so redshift determination. These are much smaller samples than all the gamma ray bursts observed by Swift, but still they allow you to really compute the physical quantities and compare them from different families in a proper way. And for example, comparing the results of the short gamma ray burst sample built this way with the initial upper limits from in 1708-17 from Swift already told us that we were looking something that was very different to the short gamma ray burst that we were observing with Swift so far. We have observed with Swift so far, and as I showed you before, in fact, we were observing an off-axis gamma ray burst. So present and future status, we are very, very lucky because today we have two great missions that join the game with Swift and Fermi of discovering and characterizing gamma ray burst that are Einstein probe and SVOM. I will say something more about SVOM in a minute, but Einstein probe, just to introduce you, Einstein probe is a Chinese mission with a contribution from ESA and MPE with two X-ray telescopes on board. One is large field of view lobster eye, and one is a sensitive narrow field instrument. And as Swift is monitoring the X-ray sky, discover cosmic variable objects of different kinds and transient phenomena that are bright in X-rays. So it already demonstrated after 1 year of activity that it discovered many, many interesting new transients in X-rays that we didn't know about. SVOM is again is a product of a collaboration between China and France. And actually here at IRAP, we have the the science center of one of the main instruments on board SBOM, which is Eclair. So SBOM is something, took somehow the legacy of Swift in trying to catch gamma ray bursts as fast as possible and to monitor them at all wavelengths possible. And how it does that? It has 4 instruments on board, 2 wide field instruments and 2 narrow field instruments. One is Eclair, which is a coded mask similar to BAT. The other is GRM with 3 detectors that have a much larger field of view than Eclair. So when a gamma ray burst explodes in the field of view of Eclair, the satellite, the combination of the 2 instruments can monitor the prompt emission from 4 keV up to 5 MeV. So it broadens a lot the possibility of Swift of monitoring prompt emission, and provides a full coverage of the prompt emission spectrum, enabling, of course, the measure of the peak of the spectrum and all the physical quantities associated. Then the satellite, if the source is bright enough, can repoint as Swift very fastly and put the source in the field of view of the 2 narrow field instruments that are at an X-ray telescope, MXT, that can monitor the X-ray afterglow from a few minutes up to its initial decay, and then also an optical telescope on board, the VT, that can monitor the optical afterglow associated to that. But together with the space segment, SBOM has also a ground segment of dedicated robotics telescopes that receive the alert that automatically repoint if possible, so that SBOM can provide really a whole coverage, different frequency of the optical afterglow, up to late times, and very sensitive. So here you can see the sensitivity of the optical telescope compared to the sample of long gamma ray burst. So SBOM mission is to get a unique sample of a number of gamma ray bursts that with prompt emission very well covered over 3 decades in energy, X-ray and optical near-infrared afterglow for most of them, and a redshift measurement for a large fraction of these events. And this will allow to probe different open questions in gamma ray burst times. Actually, since SBOM was launched in June 2024, this is not a theory, it's also reality. And I just put here as a summary slide of all the observation of the current SBOM sample. So you can take this number with cum grano salis, because we had spent a lot of time commissioning, so the pointing was not nominal and the duty cycle was not nominal, but still you can see that we are accomplishing what we wanted. So we have a lot of long gamma ray burst, short gamma ray burst, a lot of X-ray rich gamma ray burst. That is one of the science goals of Eclair, since its low energy range at 4 keV enables to study much more in detail this family compared to Swift. And 18 gamma ray burst with redshift, which is great. So I think I am finishing my time. So I leave you not with conclusions, because we don't have any for the moment, but we have a lot of open questions, which is more important and more interesting, I think. So I show you that we had 2 families of gamma ray bursts that are physically different, that come from different progenitors. We are very happy about that. It's not the end of the story. And I mentioned you briefly before this very interesting gamma ray burst, 230307A, where the precise localization from XRT enabled a spectroscopic follow-up with JWST that discovered a kilonova. Okay, I didn't tell you that this is a long gamma ray burst, it's not a short gamma ray burst. And actually, we have now a very small but interesting sample of gamma ray burst of long duration in the prompt emission with a kilonova associated. At the same time, we have at least one example of a short gamma ray burst with a supernova associated. So this dichotomy, very simple, that I presented you, that I told you in the first slide, is currently challenged by this kind of observation. Another important topic that can be explored in the future, and when we expect that the Einstein probe and SWAM will give really a great contribution in the incoming year, is on the poorly explored families of gamma ray burst that are X-ray rich, X-ray flash, low luminosity, and ultra long. I put here the luminosity function of long gamma ray burst, and as you can see, while it's very well constrained at high luminosities, it's very poorly constrained at low luminosity. So here there is really a discovery window which will be opened by the sensitivity to X-rays, better sensitivity to X-rays of Einstein probe SWAM, and we would like to fill this gap in the first few years. Another point that I briefly mentioned you before, because that would be a separate talk, actually, is the central engine of gamma ray burst. I just said that we have two possibilities explored, black holes and magnetars. There are a lot that you can do with current observations that help you to disentangle these two kind of progenitors, and we already did that a lot with Swift data. Unfortunately, the smoking gun for the nature of the central engine cannot probably come by electromagnetic observation, and this is another topic where the other messenger can help us, in particular gravitational wave, because probably the smoking gun for the nature of the central engine can come from the observation, for example, of the post-merger signal in gravitational wave from the coalescence of two compact objects with two neutron stars. One black hole is, of course, a black hole. And this is possibly not achievable with current interferometers, but that could be achieved with Einstein telescope. This is maybe an old plot, but still it holds. And also, as I said, with our current understanding of the jet structure comes from one single observation of this 170817. So other multi-messenger events will help us also in this science case, but we can have also other electromagnetic complementary observation. For example, we need to improve our ability to recognize often afterglows, so afterglows that are seen so faxes that you don't catch the prompt emission, so you don't have the high energy trigger, but they are hidden in surveys in optical or radio. And already in ZTF, which is an optical survey, 6 possible orphan afterglows have been spotted with Rubin, and in radio with SKA, we expect to have many, many more orphan afterglows, so we have to learn how to recognize them. And there is a talk about that in coming days by Marina. So this is the open question for the future. We have a lot to do. Thanks a lot.
Grazia, for his very nice talk. So, is there any question for Maria Grazia?
Caterina.
Hi, thanks a lot. Just for I mean, I know nothing of this part, so probably it's very trivial. But so you were saying that for the long GRB, you need to have at least one progenitor that is a neutron star. One of the two compact objects that is a neutron.
Short gamma ray burst, you need that.
For sure, sorry. Yeah.
The merger contains at least one neutron star, because in the end you want a compact object with some matter to be accreted. Yeah. So.
And is there a way to, I mean, now that you have also the GW counterpart, is there a way to understand what is the other progenitor from, I don't know, the luminosity, the energy, or do you have to just go to necessarily go to the shape of the wave, of the gravitational wave?
I think that maybe gravitational people can tell that better, but I would say that from electromagnetic point of view, there is not so much that you can do with luminosities and so on to really probe the nature of the progenitor. You just can have this indirect observation of other transients associated to the same progenitor. So if you have, for example, a kilonova like in this event, which despite being a long duration gamma ray burst, you see a kilonova, you know that there is a neutron star there. So it comes from the merger. Let's, in a very general way, there are also proposals that also supernovae do some are processes. So I'm not expert in that. Probably Daniel will tell you better later.
Thanks.
But yeah, with electromagnetic, we can only have indirect proof because we are observing actually the jet from the dissipation in the jet very late. So we had to reconstruct what happened at the very beginning.
Was there questions?
Thanks for this nice overview. I have a question that is probably a naive one. So the gamma ray burst associated with 170817 is interpreted as structured and offset, and it was very faint. Yes. But I expect then that most of the short gamma ray bursts that we observe are offset. So are there any studies that try to identify those and maybe after 170817 and to quantify how many we missed or misidentified?
I know that there has been a study in Fermi collaboration. So they try to look at like faint or subthreshold short gamma ray burst that present a characteristic similar to the prompt emission of this, and they found a few of them. Unfortunately, since Fermi is only is a triggering facility but has no repointing capabilities, we don't have follow-up for those. So we have just the prompt emission. So it's important to underline now that, as you mentioned, this gamma ray burst was very weak and very uninteresting from the prompt emission point of view. So without the gravitational wave signal, no one would have cared about that. Yeah. So probably some of them are just missed, and we have no multi-wavelength information and no redshift measurement and so on. For the well studies short gamma ray burst, I do not expect that many of them are this way, because actually when we look at them in X-rays and we see them like that, we are sure that they are slightly on axis, let's say. You see that this is very different and very peculiar.
Yeah, so those that we identified as short gamma ray burst, yes, but I was wondering whether also the, starting from the paper that you mentioned, maybe I will ask you the reference, if they try to estimate whether the number that they retrieved a posteriori is consistent with the bias
yes,
of...
They do, but I don't remember the number. It's a
okay,
small
thanks.
percentage. Maybe Paolo knows. How many in the GBM catalog?
Isn't part of the point here also that it was so weak, right? The only reason we saw it was because it was 40 megaparsecs away. So the chance that there's just no volume of space in which for these things to occur. So I don't think, to me, there's this massive missing population that were detectable just because the weakness versus distance argument. You know, I mean, I know what you think of it, yeah.
Yeah, but actually the aim of retrieving and studying off-axis orphan afterglows in other surveys at other wavelengths help us also to constrain the true rate, because not having strict information on the jet opening angle and so on prevents us from drawing conclusion on the rate. So we don't really know how many. 13.
Yeah.
The discussion.
I had another question. Thank you very much for the nice talk on SWAM. So you mentioned also often afterglows, and I was wondering about the observational strategy. So how does the trigger strategy compare to Swift, for example? So I was wondering, for example, like should we have another event sort of more or less close by, and it's maybe an often event? Can you trigger it easily to look into the UV and the afterglow without X-ray triggers? And so can you trigger on something else than gamma rays and X-rays? And how does it work?
Olivier is more entitled than me since he's the PI of Eclair. So
is much more into SVOM. I don't think we cannot trigger without the eclair trigger. So unfortunately,
Okay.
no. But there is the optical monitor on ground that maybe serendipitously is not very sensitive, but maybe serendipitously catch some other kind of emission.
So on them, we could do two things. We have the GRM, so the gamma ray monitor, that basically is a spectrometer, so it is able to detect a lot of GRB, but a very poor localization or no localization at all. An eclair, a coded mask, that could provide good localization. And the point is, in general, if you want to slew and do all the nice things Maria Grazia told you, but we need a precise localization. So we are restricted to this. So let's thanks again, Maria Grazia.